Oh, okay, let's continue. In the previous part, we had a look at piece of code uh, that used the NICO to deal with inter-node GPU communications. Okay, uh, this is the code we have discussed in the previous part. They are dealing with. We have 8 GPUs. The 8 GPUs the 8 GPUs need to have some kind of collective communication, and that's mainly the purpose of the NICO communication library. That's to deal with the collective communications. The previous part, the example shows how the programmer is going to program um, a system with intra-node GPU collective communications by using the NICO. And this section, we are going to have a look how the programmer need to use the NICO to deal with inter-node NICO communications. Okay, just a few comments is that NICO cannot work by itself. It depends on MPI library to function correctly. So it depends on the MPI. And NICO is not doing all the communications. NICO focuses on the collective communications or reduce or gather this kind of communications. There is no point-to-point communications functional call in the NICO library. So you have to use the two communication libraries together to make your code work. We are going to have a look how a programmer is going to program the inter-node communications using NICO plus the help of the MPI library. Okay, so just another comment is that MPI is a traditional communication library that's used to deal with communications between the nodes, between the hosts. Okay, and the NICO is used to deal with the communication between GPUs. The GPUs could be across multiple nodes. So they are different. They focus on different kind of communications. This is for host, for CPU communication, and this is for GPU. Okay, and it is for GPU and it is for collective. Is called collective communication. Okay, we are going to find out more details later on, but now let's move on to a piece of code. And in this piece of code, we are going to find out how a programmer is going to use NICO to deal with communications between GPUs connect to different hosts. Okay, for this piece of code, the starting point is here. This is the main function. This is the starting point of this piece of code. But here, there are some macros and functions. We just go through them very quickly. They won't affect our discussion, but it's useful to understand what they are doing. Here, MPI check, CUDA check, and NICO check. These are the error handling macros. We are going to see them in the code. We are going to have a short explanation when we are going to meet each of them. And then there are three functions defined: the get hash function, the get hostname function, the get hash function, and the get host hash function. These functions, we don't dive into the details of these functions. We just try to understand what the functions are going to do by reading their name. Now, what they are going to do is exactly as their name is get hostname, host hash, and get hash, etc., etc. And here, I'm sorry, I copied this get hash twice, so we just need to remove this one. You forget about this one. And the piece of code starts from this main function. To make our discussion more easier, more easier to understand, what I have done is that I just removed all these macros and the functional calls, the function definitions. We start from this main function. I put the system drawing our scenario just alongside this piece of code to make things easier to understand. Okay. Suppose we have the scenario, which is you have 4 MPI processes, you have 4 MPI processes, you have another 4 plus 4 MPI processes, 4 MPI processes per CPU. You have 4 CPU, you have 16 MPI processes. You launch the code. You are going to launch this piece of code on these 16 MPI processes. Pretty much you are going to use, let's see, 16 cores. Okay, and this, the configuration of this MPI process is that this piece of code, you are going to have multiple MPI processes. For our case, we have 16. And each MPI process is going to work with only one GPU. In the previous part, we have seen that one process could work with 4 GPUs. But this one, to make things easier to understand, I have chosen this piece of code, which use only one GPU per MPI process. Okay? So you have 4 MPI processes per host, and you have 8 GPUs. So each MPI process is going to work with only one GPU. Your MPI process will be with different ID, start from 1, 0, 1, 2, etc., etc. And here you have 7. So this MPI process is going to work with GPU 0. This is the C program, so we have to do give the ID like this, and this is the 7, not 8. And the 7th MPI process has to work with the no, not the 7th. The 8th MPI process has to work with the 8th GPU, but both of them has the ID of 7. Okay. The MPI, this piece of code will be launched on the 2 nodes, and you are going to have, let's see, 16 MPI processes. Pretty much the 16 MPI processes will be running on 16 cores. And each, at the beginning, each MPI process, they are going to declare some variables. The size is the size of the array. Okay, maybe it's a good idea to have a look of the math of this piece of code. This piece of code is doing exactly the same thing as the previous code. The previous code, what we did is that we have 4 GPUs. Each GPU is going to have an array, and we are going to do an all reduce of the array, the 4 arrays hosted by the 4 GPUs in their memory. In this example, the mathematics is the same. We are going to have one array per GPU. The array is a 3-dimensional array. This is the size of the array, and each GPU you are going to have one array in the GPU's memory. So for our case, we have 16 GPUs. We are going to have 16 arrays. And we are going to use the NCCL to do an all reduce operation on these 16 arrays. That's the mathematics. In the previous part, in that example, what we did is an all reduce operation between 4 arrays in the memory of 4 GPUs. Here you have 16 arrays in each array in one of the GPU's memory. So you have 16 arrays. You are going to do an all reduce. So you have an array here. You have another array here. Okay, this three-dimensional array. So you have another three-dimensional array. Three-dimensional array. I'm drawing a cube to show a three-dimensional array. Okay, you are going to do the all reduce between all these arrays. Okay, this is the mathematics. Okay, let's start. Okay, as I just mentioned, that NICO depends on the MPI library to function correctly. Without the help of the MPI library, NICO doesn't work. NICO depends on MPI. MPI could help NICO. So you are going to say that for this piece of code, the first functional call is not NICO, it's always MPI. For MPI communication, the starting point is that you need to call this MPI initialization functional call to build up the communication structure. This is the functional call. MPI check, this is the arrow handling macros. If you call this MPI initialization, you get an arrow comes from the system. You have to deal with the arrow message. So you have all this MPI check to deal with the possible arrow message. If there is no arrow message, everything will be fine. I suppose for our case, everything will be fine. So at the beginning, you initialize your MPI communication. You build up this MPI communication structure. After you have built up this communication structure, you need to make this MPI functional call. The first one is that you are going to launch this piece of code on 16 calls. And each call is going to have an instance of this piece of code. And each MPI process, they are going to have its ID. MPI ID is the my rank. So my rank is the ID. If each rank, each MPI process is going to have a different ID. The first one is going to have ID 0. The second one will have ID 1, and third will have ID 2, etc., etc. And the 16 MPI process is going to have the ID 15. We are in C. It's like this. And each MPI process, they need to know how many processes are going to be involved in this communication. So here you need to have the number of ranks, which is 16, because you have 16 MPI processes. Okay, after these 3 lines of code, the MPI communication structure has been built up. The 16 MPI processes running on the 2 hosts, they can communicate each other by using the MPI library. As I said just a moment earlier, is that for the NICO communication, to use NICO, now you don't start with NICO, you always start with this MPI functional call. Okay? And these 16 MPI processes, each one is going to declare an one-dimensional array, host hash. The host hash one-dimensional array is going to have 16 elements. The same quantity of elements as your MPI processes. You have 16 MPI processes. You are going to have 16 elements for your one-dimensional array called host hash. And it's not this one, each MPI process is going to declare 1. So you have total 16, because each MPI process is going to declare 1. And you have 16 MPI processes. You are going to declare each MPI process is going to declare 1. At the end, you are going to have 16. And this 16 belongs to different MPI processes. Example is here, is that this first one belongs to MPI process 0, the second one to 1, the third one to 2, the last one to 16. Okay? And then each MPI process is going to declare a variable which is called host name. Okay? And then each MPI process is going to call this function get host name to get the host name. For our case, we have two hosts. The first host, the host 1, and the host 2. So where each MPI process is going to get the host name. So the first 8 MPI processes running on the first host, they are going to get the host name of the first host. The second half MPI processes, they are totally 8 MPI processes. They are going to get the host name of the second host. Okay? And then each MPI process is going to use get host hash function to work out the host hash of each MPI process, because this is going to be done 16 times because you have 16 MPI processes. MPI process 1 is going to work out a host hash here. And the others, it doesn't care for the moment, is going to be an invalid value. It's going to be a rubbish there. And the second MPI process, which is going to work out its host hash, is going to put it here. And all the others, it doesn't care. And the same thing is going to happen with the third MPI process. Is going to work out its host hash. It's running on a host. It can do the host hash based on the host name. It's very simple. So it's going to work out this one, the third host hash. The others, it doesn't care. And the last MPI process is going to work out this host hash. And it doesn't care all the others. Okay? And right now, we know that each MPI process has declared a one-dimensional array, and there is only one element valid worked out by the MPI process. All the others are not valid. Now, what we need to do is that we need to make sure that each MPI process is going to have a complete one-dimensional array with the host hash of all the 16 valid host hashes worked out by this MPI process. So what we are going to do is that we are going to call this MPI algorithm functional call. We are going to work with these host hashes, and we are going to do in-place algorithm. What are the MPI processes are going to do is that MPI process 0 has to send its host hash to all the others, and it is going to be put in the first position, is element 0. And the second one is going to send its hash, its valid element to all the other MPI processes and put it in the right place. For this one, is going to be in the second place. Okay? In the second place. That's for MPI process 1. MPI process 2 is going to send its valid host hash in the third position of this one-dimensional array, and is going to be in the third position of all the array, all the one all the to in the third position of all the other one-dimensional arrays. And there's going to be the same for the last MPI process. Is going to send its valid host hash to all the other MPI processes, and that's going to put in the last position. So after this has been done, then each MPI process is going to have a valid, is going to have an one-dimensional array with 16 elements, and each element is a valid host hash of the host name that the MPI process is running on. So here, this is this is the one-dimensional array with, for our case, is from 0 to 15. You have one-dimensional array, and the first element of this array is going to be host hash 0, and second one will be host hash 1. The third one will be host hash 2, and the last one will be host hash, for our case, is 15. Okay, you have each MPI process is going to have this array, and they are holding they are exactly the same. They are holding the same host hash value. And then this is for the MPI process. For the MPI process, now we need to work on this local rank. What's this local rank? Oh, this local rank is the ID of the GPU. So it's GPU ID. At the beginning, the local rank is always 0, is the GPU ID. Suppose if you have 16 nodes, you are going to run this piece of code on 16 nodes, and on each node you have only one GPU. That GPU will be having ID 0. So that's the reason why at the very beginning the local rank is always 0. So the GPU ID at the beginning is 0. Okay, and then this piece of code is to work out the GPU ID for each MPI process. We have 16 MPI process. Each one will work with only one GPU. Okay, we take this as we take this as an example. Here is that you have for this node, you have 8 MPI processes. You have 8 GPU, and each MPI process is going to work only with one GPU. So you need to have a way to distinguish these 8 GPUs that are working, each one are working with only one process. Now in this picture, what I'm trying to see that MPI process 0 is working with GPU 0, MPI process 1 is working with GPU 1, MPI process 2 is working with GPU 2, and then MPI process 7 is working with GPU 7. But we need to make sure the system knows it. So this piece of code is doing exactly this one. We have a look at this one. Each MPI process is going to execute the same line of code. So I have MPI process 0 comes in, MPI process 0 comes in, and my rank is 0. My rank is 0. And we are going to loop over all the MPI processes. And the first loop we are going to have this P is 0 because we start from 0. And MPI plus X0 is running this for loop. And the first loop is going to say, okay, now right now P is 0 and my rank is 0 and my rank is the same as P and I'm going to break. I'm going to do nothing. The for loop will be broken. And it is going to jump out of this for loop. And then we are going to have the local rank of MPI process 0 being 0 because the initial value is here, is 0. Okay? And then if my rank is 1, okay, my rank is 1, MPI process 1 comes in, is going to run, is going to execute the same for loop. Okay, so the first loop is loop over value 0. Okay, value 0 and my rank is 1. It doesn't equal this 0. So I'm going to run the second line, this if line. Okay, if my if host hash 0 equals host hash 1, the local rank will be increased by 1. What does that mean? That means if MPI process 1 finds out that is host hash 1 equals host hash 0, and then this local rank at the beginning, the value is 0, is going to be increased to 1. So now we understand that for the second MPI process, because it is located on the same host, so their host hash is the same. But the second MPI process cannot work with GPU 0 because it has been decided that GPU 0 is going to work with MPI 0. So this one, and then the system is going to decide that, okay, MPI process 1, you have to work with GPU 1 because it means the second GPU. Okay, so we continue. The third MPI process, which has ID of 2, is going to loop over this for loop 2 times for 0 and for 1. If P equals 0, the local rank will be increased 1. When P equals 1, the local rank will be increased another time. That's 1. This is 1. It's going to be increased another time. And the third time, the P will be 2, and the for loop will be broken. And the loop, the MPI process is going to jump out of this for loop, is going to stop. And the local rank will be 2. That happens with this one. Okay, so now it's clear what this for loop is doing is to assign each MPI process a GPU to work on. And the local rank is the GPU's ID. Then that means for the first 8 MPI processes, because they are running on the same host. So the first 8 host hash will be the same. Okay, that means the first 8 MPI processes, they are going to have their local rank starts from 0, ends with 7, because we have 8 GPUs per node, ends with 7. So by going through this for loop, finally we are going to tell the system, we are going to tell each MPI process running on the first host. We have totally 8 of them. Each one, they are going to know which GPU they are going to work with. That's going to be from 0 to 7, 8 GPUs. And that's for the first node. And then for the second node, this piece of code, this for loop, for the second half MPI processes started from 8 up to 15. You have another 8 MPI processes, and they are running on the same host. Their host hash will be the same. And then at the end, started from MPI process 8 to 15. Each MPI process is going to have their local rank. Start again from 0 and end with 7. Okay, so this piece of code basically is telling the 16 MPI processes you need to know which GPU you are going to work with. And at the end, the final result is that the first 8 MPI processes, each one is going to work with a different GPU, and the GPU need to be distinguished with the local rank, with the GPU ID. Okay, and the second host is the same thing, the same story. This piece of code is a little bit tricky, but we try to understand it. Now we can understand what it's doing. Now let's continue. Let's come to the main part, which is the calculation. We are going to get into this NICO communication part. I'm going to change the color to blue to show this is the NICO. For the NICO communication, first we need to work out this NICO ID. So right now we are going to declare all the variables we need for this NICO communication. So NICO ID, NICO communicator, and the send buffer and the receive buffer. Well, the buffer is going to the buffer we have discussed in the previous code is that the buffer, basically this is the buffer. Buffer is one-dimensional array of pointers. You have 16 GPUs. You have 16 GPUs. You are going to have 16 buffers, 16 elements. Now you have one-dimensional array which hosts the pointers of the buffers. You have 16 GPUs. Your one-dimensional array is going to have 16 elements, and each element is a pointer to the GPU to the location where you are going to have the array. So this is something we discussed in the previous part. And this the send buffer, receive buffer, which is the pointer, and then you need to declare another variable which is called stream. Now we just omit we pass this stream. Just remember that stream is something related with the GPU computing. When you offload your workload to the GPUs, you need to tell the GPU the stream. We are going to pass this discussion. I'm trying to make things simpler because I want to focus on this NICO communication. So we just take it for granted that each time we offload the workload to the GPU, we need to tell the GPU the stream. Okay, but there is a way to work it out. So these are the variables. Now, what we need to do is that we are going to work on this unique ID, unique NICO communication ID. And this ID, it doesn't need to be worked out by the 16 MPI processes. Only one process is MPI process enough. So the programmer has decided that, okay, you have 16 MPI processes. Only the first MPI process your rank is 0. What you need to do is that you need to call this Nico get unique ID function to find out this ID, this Nico communication ID. Okay, and then it has been done. You have got this ID. We need the help of the MPI library again. Is that I need this MPI to broadcast this ID to all the other MPI processes, because only the first MPI process has worked out this ID. So it needs to be broadcasted to all the others. So all the other MPI processes, they are going to know this Nico ID. So this is the MPI broadcast. And we are going to broadcast this ID, and you have all these parameters to make this functional call successful. So the ID, the Nico ID, has been broadcasted to all the other MPI processes. Now it seems we are ready to do the Nico communication. Not quite yet. We need to prepare for the GPU computing. Okay, now we come to this part, is that each MPI process, you need to get the right GPU that you need to work with and allocate the memory. So I've said that the local rank is the GPU ID. The GPU ID, okay, each MPI process you need to work with only one. Which one you need to work with, it has been found out by this local rank. So, okay, we have 16 MPI processes. The first one is going to work with GPU 0, but this GPU is in host 1, and the second MPI process is going to work GPU 1. That's in the first host, etc., etc. And the 8th MPI process is going to work with the 8th GPU, which has the local rank 7. So for the first 8 MPI processes, they are going to work with GPU 0 to 7 connected to host 1. And then MPI process 8 to 15. Another 8 MPI process, they also need to work with GPU 0, 1, 2, up to 7. But here, these 8 GPUs belongs to host 2. That explains why their local ID are the same. You have twice GPU 0, but they belongs to 2 different hosts. Okay, so using this local rank, each MPI process is going to find the right GPU they need to work on, and then each MPI process is going to tell the system, okay, I'm going to work with my target GPU with local rank. And then each MPI process, they need to declare a piece of memory to hold the array, and this memory will be from the GPU. So the array, this array will be in the GPU memory, and these are the lines of code that the programmer uses to ask for the memory from the GPU. Okay, and then you have this stream stuff here, and then the memory has been declared. Right now, the each MPI process, they are going to have a buffer. They are going to have a buffer which hosts the pointer, and the pointer is going to point to the address allocated on the GPU in the GPU memory. So, and then now suppose we right now we can work with data. This piece of code, it seems it has been allocated the send buffer and the receive buffer, and the data. I mean, the array has been declared. The data has not been the data has not been initialized. Anyway, that doesn't affect our discussion. The array has been allocated, but the value of the array has not been assigned. So the array basically is holding some sheets. So what we need to do pretty much here, we need to set the we need to set the here we need to have some line of code to set the values of the array. So we need to set the values of each three-dimensional array. Okay, but okay, anyway, it doesn't affect our discussion. Just you remember that you need to set the values for this array. If you don't do that, the code is going to give you some not meaningful results. But anyway, it doesn't affect our discussion. Okay, after this, the values of the array has been set. Right now, we are ready to start this unequal communication. Let me change the color. Okay, what we need to do, the NICO functional call, the NICO communication library, the usage of the NICO communication library is nearly the same as MPI. So what we need to do is that first we need to initialize the NICO communication. We need to build up this kind of NICO communication structure. So we need to call NICO communication initialization rank. Okay, so this is the functional call to build up this NICO communication structure. We need to tell the NICO communicator to pass the functional call the NICO communicator, and we need to tell the NICO communicator how many MPI processes will be involved in this functional call, and what's the ID of the NICO communicator, and because each one of the 16 MPI processes, they need to call this functional call. So you need to tell the functional call what's your ID. So 16 MPI processes, they are going to do the same thing. Okay. Each done, everything is fine. Right now, we are ready to use this NICO functional call to do the collective communication, which is NICO or reduce collective communication. So you call this NICO or reduce functional call. You tell this functional call you are going to work with send buffer with the receive buffer, and you need to tell the system the functional call, what's the size of the array, and what's the data type in this array, and what's the or reduce operation you need to have, which is sum for our case, and this is the NICO communicator. And there is a stream S for the GPUs. Okay, so this is the functional call. At the end, we have gone through all these lines of code. At the end, we can start this NICO communication. We can start this NICO or reduce. That's what we want to do. So this shows you also the complexity of this NICO programming, because all these lines of code which are preparing for this communication, for this collective communication. Okay, so we call this function to make this to start this or reduce collective communication, and then I have started this collective communication. We need to check, to synchronize, to check whether it has been started successfully without any trouble. So we need to call this CUDA stream synchronize to check whether everything is going fine or not. Okay. If there is no error message from the system, that means everything is fine, and then the NICO is going to do this all reduce functional call, this all reduce collective communication for you. And after these two lines codes, is supposed that your all reduce communication has been successfully finished without any error. If you have no errors comes out from the system. Okay, now the all reduce functional call, the all reduce collects communication is done. After your communication has been done, here still we miss some codes, because after this communication has been done, the results will be still in the array in the GPU memory. What we need to do, basically here, we need to add some lines of codes. You need to copy the data, I mean the array, the data back to the host memory, copy data to host. Basically, something we need to do. If you don't do that, I mean, here you have two lines of code, which is related with GPU computing, and you are going to free the memory that's holding the arrays. If you free this array, you are going to lose all the data in that array. So what we need to do is that we need to copy it back. So what I mean is that there should be a line of code, a few lines of code to copy the data back. But anyway, it doesn't affect our discussion because we focused on the NICO communication, and from the point of view of NICO communication, it's a piece of complete code. And then you free these two buffers, and then right now you have finished your all reduced collective communication. What you need to do is that you need to destroy your NICO communicator, because you have built up this NICO communication structure. You need to use the finalize functional call. I mean, you need to finalize the NICO communicator, the communication structure. You need to destroy it. Okay, and then with the fact that you have finished this NICO or reduced collective communication, you do need to use this MPI communication structure anymore. You need to do the same thing. You need to call this MPI finalize function to destroy your MPI communication structure. Okay, and at the end, if you want to output your results, it's your responsibility to output results. Okay, now let's do a very quick summary. Here is that we can say that for internode GPU communications, for internode collective GPU communications, you need to use this NICO library to deal with that. You need to use NICO, because NICO has the possibility to do the communication going through three kinds of network technologies. As I said, that's the reason that Nvidia has to reinvent the wheel, which is the NICO communication library, which is very similar to the MPI communication library. And the second point we can understand from this piece of code is that NICO communication library for GPU, it depends on the MPI to function correctly. Without MPI, it doesn't work. And here, MPI is here to help the NICO communication to happen. At the end, what we are going to do, each programmer has to do is account for mix of the MPI library call and the NICO library call. You have to use these two communication libraries to finally make your internal GPU communication happen. It's not easy conceptually, but if you have got this basic idea of this MPI communication for the CPU computing, no, it's not too much difficult to pass to the step to understand the NICO communication. As said by Nvidia, NICO is a kind of complementary to MPI library because NICO is dealing mainly collective GPU communications and MPI is doing communications between the hosts. And sometimes the MPI library can also help to deal with the communications between the GPUs because NICO doesn't deal with point-to-point communications. It deals only with collective communications. So the summary is that you need to mix the two communication libraries to make this inter-node GPU communication happen. This is what the programmers need to do to make the code work. Okay. Up to now, we are reading this short piece of code to understand how to use the NICO communication library. In the next part, we are going to have a look of this NICO communication library implementation details. And by understand these NICO implementation details, we are going to understand more better these two pieces of codes. Why the programmer are writing this code like this? Why they have to write the code like this? Okay, let's have a 5 minutes rest, and then we are going to come back and continue our discussion. I'm going to stop our recording and see you very soon.